This conference will now be recorded.
Good evening, students. Welcome to the PYQ discussion sessions. So we have been discussing JEE main question papers. We had discussed question paper 2020, the JEE main papers during the September session. We had already covered 2nd September, 3rd September, 5th September, and few questions remaining from 6th September paper. And today I'll complete this and catch up with or start with the 4th September papers. Okay, so let us. So this is a problem from 6th September second shift paper. So this question says, in a LR circuit, power of 400 is dissipated from a source of 250 volt and 50 hertz frequency. The power factor of the circuit is given as 0.8. So this is for LR circuit. In order to bring the power factor to unity, a capacitor of value C is added in series with LR. So the question is actually saying that you had simply LR circuit first and parameters are given, and for that the power factor cos phi is given as 0.8. Okay, now to make this power factor unity, one capacitor has been added in series with the existing this LR circuit. Okay, all right. In order to bring the power factor to unity, a capacitor C is added in series to LR, taking the value of C as this microfarad. Okay, N by 3 pi microfarad. Then the value of N is dash. So you have to find out what is the value of N. Okay, so you have to find out in integer number to fill up this blank space here. So look, first of all, let me write down what are the informations given. So power is given, okay, and voltage is given as 250 volt, and this frequency is given, power factor is given. Okay, so you know what actually RMS power means. So power is actually given by ERMS, okay, ERMS, IRMS, and cos phi. So this is one formula. Okay, so ERMS is given here, so that is 250. So ERMS, IRMS I can write, see, IRMS I can write further ERMS by Z, and this is cos phi. Okay, so see, this is ERMS square by Z into cos phi. So this is given as actually 400 watt. Okay, so look, we have to find out first Z. What is Z? Okay, so Z, see, Z is given by this ERMS square by 400 into, so ERMS is given as 250, square of that divided by 400, and cos phi is given as 0.8. I am writing here this. Okay, let us see how we get from here, see this 250 into 250 will give you 6250. Okay, and along with that there will be two zeros, since I am okay. So this 250 square I have written here as this. So these two I can just strike them out. Okay, now look. So I can actually divide with, see, this 4, this is 5, this 4 cancels each other, and then see this I will get 125 ohm. Okay, so what we get? We get Z as 125 ohm. So from the given informations, I have got Z. This is for LR circuit. So in case of LR circuit, what is Z actually? Z is XL square, square root of XL square plus R square. Okay, this is what we know. Okay, this is the impedance, and from the given informations we have found out this. Okay, now you have to find out capacitance in the LCR circuit. So in that case, what is, okay, so from here let me first find out what is XL square, sorry, R square. Okay, L is also not given, XL is also not given. We know this cos of phi is equal to R by Z. If I know the Z, then I can find out R also. Okay, look, I'll just do that first. I'll find out R first. Okay, R means Z into cos of phi. So Z is 125. Z is 125. We have calculated that. Okay, let me just go here. So R is Z into cos of phi. Z is 125 ohm and cos phi is actually 0.8, that means 8 by 10. So this is 2. If I just divide with 5, so this is 4. So we get this resistance of the circuit also. So we have got Z to be 125 ohm, R is equal to 100 ohm. Then what is the difficulty in finding out XL? No, there is no difficulty, right? So XL is Z square minus R square. Okay, so Z square minus R square is equal to XL square, right? So this is what I can do. So XL square is 125 square minus 100 square. Okay, see, look, what I can do is 125 I can multiply. Okay, to solve this easily, I'll just write double like this. Okay, and now see, I can take few things common here. I can take, see, I can write this 25 into 4, and this also I can write 25 into 4. Okay, and here I can write 5 into 25, and this 125 I can write 5 into further 25, right? So you look, I can get 25 square common out of it, and this is 5 square minus this is 16, right? So you get 9 into 25. Okay, now take this square root of this will be, so XL will be 3 into 5. Okay, 3 into 5. So that is actually 15. 15. I hope there is some mistake I have done. Okay, sorry. This is actually 25. 25 square, so it will be 25 only. Okay, so 25. So this will be 75 ohm. Okay, so I have got XL also. I have got XL. I have got R. Okay. Now see in the second case. Okay, let me write down what I have just found out. This to be 100 ohm. This Z is 125 ohm. Then XL we have found out 75 ohm. Okay. Now we have to find out what is, see, Z in case of LCR circuit will be XL minus XC, okay, whole square plus R square. This is one point to think of. Now another point is, see here, for the after adding the C, your power factor is becoming unity. Unity means cos phi is equal to 1. So this is where we have to get the point. So when, so you see again, cos phi is equal to R by Z. Okay, R by Z. Okay, R by Z. See, if R by Z has to be equal to 1, then R has to be equal to Z in case of LCR circuit. Okay, impedance has to be uh, equal to the resistance, and that is possible. So this is possible only. So this is possible only when XL is equal to XC, right? So now we know the XC, value of XC. I have to find out, sorry, I know the value of XL. So that is XC also. So this is this much. Now XC means 1 over omega C, or that is equal to again 1 by 2 pi F C. Okay, that is equal to 75. So if I want to find out what is C, then look, C is equal to 1 over 2 pi. 50 is the frequency, right? 1 by 2 pi F into 50 here. Okay, I hope I'm all right. 50 hertz, fine. Yes, so these are fine. So, and this is nano n by 3 pi. Okay, n by 3 pi. So n by 3 pi. Let me write n by 3 pi here just to compare. N by 3 pi, right? See, I'll just clean little bit here because there is going to be little bit lengthy calculations. Okay, here, see, we have C is equal to 1 over 2 pi 2 pi into 75 into 50. Okay, all right. So Let me make first in terms of this unit is like this is given as this much, okay, and this is picofarad, right? Microfarad, okay, 10 to the power 6 in terms of 10 to the power 6, okay, like that it is given. So let me multiply 10 to the power 6 first of all, okay, 10 to the power 6. Then let me keep this 3 pi here, 3 from here, so 25. I will have here 2 into 25 into 50, right? So this microfarad 10 to the power minus 10 to the power minus this, to get 10 to the power minus I have to multiply 10 to the power 6, okay, okay, so this is now microfarad in terms of microfarad, okay. So I have, see, this much is the unit of, so this is unit of microfarad, and this is I have got here, it is microfarad, okay. So 10 to the power minus 6. All right, so here look, I'll write 10 to the power 6, right? So I'll write in terms of 10 to the power 2, 10 to the power 100, 100 and 100. Let us see if you can simplify in this way, okay. This is microfarad, so I'm not writing this 10 to the power minus 6. 3 pi I'm writing here, 2 I'm writing, 25, this is 50. Just for the sake of calculation I'm writing this way, otherwise you can directly do it. See, this will be 4, so this will again make it to 2, this will make this 25, okay. So here there will be 100 only, so this 25 will make this 100 as 4, okay. So you look here, what I get is 400 by 3 pi, and this is in microfarad, okay. So it may be becoming little bit hazy, but I hope you have understood the way I have done here. First of all, you have to find out what is Z from the given informations, from the given power and the power factor for the LR circuit, and then we have to find out, see, from cos phi R by Z. So once you get Z, you can find out R to be equal to Z into cos phi. Once you get R, you can find out what is XL. So you get these three things. In case of LCS circuit, you will have impedance is equal to square root of R square plus XL minus XC whole square, okay. But in the LCS circuit, the cos phi is given to be 1, and that is equal to R by Z. So R has to be equal to Z when these two will cancel each other, okay. So that's why we have written XL is equal to XC. That means at the resonance condition it can happen, okay. So power factor will be unity at the resonance condition for this particular circuit when the capacitance value will be 400 by 3 pi microfarad, okay. This should be the capacitance value. So look here, n by 3 pi mu farad, so n will be 400. All right, let us go to the next problem. So let us go to the next problem. So this problem is also from 6 September 2020, shift 2 paper. Young's double slit experiment is performed using monochromatic light of wavelength lambda. The intensity of light at a point on the screen where the path difference is lambda is k. See, we know this uh, intensity where, like, if the path difference is given as some lambda, we can find out the phase difference. So in terms of phase difference, it will be some 4 a square cos square phi. Okay, kind of this cos square, I think cos square phi by 2. Okay, all right, so this is the kind of formula we have, and this I can take as some constant value. This is the maximum value, or I0 or k, whatever it is. Now if we know, see, path difference, let us see this. When the path difference is lambda, see, path difference is lambda, then how do we get the phase difference? Phase difference is equal to 2 pi by lambda into lambda. Okay, so 2 pi by lambda into lambda, so this will give you phase 2 pi, and see, 2 pi by pi by 2, then it will be pi. Pi means cos pi means, so cos pi means 1 minus 1, and square of that will give you the maximum one. Okay, so maximum value is 4a square. So this is given as k units. Okay, this is given as k units. Okay, now you have to find out the intensity of light at a point where the path difference is lambda by 6. So path difference, where the path difference is lambda by 6, what is the phase difference? Let us say that is pi prime, and that is 2 pi by lambda into lambda by 6. Okay, cancels each other, so this will be pi by 3. So pi by 3 means 60 degree. Okay, 60 degree. So cos of 60 degree divided by 2, that means cos of 30 degree. Cos of 30 degree is equal to root over 3 by 2. So you look here, what you get, I is equal to this term is there in front, and square of this. So this is actually 3 by 4. So this is actually 3 by 4. Okay, so I get 3 by 4 into this k. So we have to find out the intensity of that in terms of this nk by 12. What is this nk by 12? So I is given as nk by 12. That means, n by 12 is equal to this 3 by 4. So what is this n then? 3 by 4 into 12, which will give you 9. So n is equal to 9. Okay, this is the answer for this question. So with this, the 6th September paper is over. Now we'll continue with 4th September shift 1. Okay, shift 1 paper, shift 1, 4th September. So this question is from the very first chapter, units and measurement. A quantity x is given by this. So x is given as I f b square divided by w l to the power 4. Look here, this I is moment of inertia, this f is force, then V is the velocity, W is the work done, and L is the length. Now you have to find out the dimension of this X. See, moment of inertia, we know it has a dimension, moment of inertia, m into r square, right? M L square. Then force, we know m L t to the power minus 2. V square, V we know, so V square has unit, sorry, L t to the power minus 2, L to the power minus 1. So L square t to the power minus 2, this square. L t to the power minus 1. So I have to take square of that. And work done, you know. Okay, let me simplify. It will be, see, this is, you know, this is F, this is I, V square. I can simplify this work done to be F into L further. Okay, then life will be a little bit easier. So this F I can just strike out. Okay, now look what I have. I have this m L square, and here L square t to the power minus 2 divided by L to the power 5. So what we have here, so this 4 will cancel with this, so 1 L will be there in the denominator, t to the power minus 2 will be there. Okay, so m L to the power minus 1 t to the power minus 2. So look what I can write. I can write ml 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 t to the power minus 1. Okay, just I'm writing ml t to the power minus 1. So this is force. Okay, so I have L to the power minus 1. To make it L to the power minus 1, I have to write here L to the power minus 2. Okay, ml t to the power minus 1, and here t to the power minus 1 again. Okay, so this is force. Say ml to the power minus 1, this is force. Okay, force into this is, say, this one. I can write L to the power minus L to the power minus 1 divided by L cube. Look how it is. So L to the power minus 1 is actually velocity. So force into velocity is power, right? Divided by this. So energy, so it is going towards energy density. L to the power minus 1. Sorry, this is, see, I have L square. Okay, look, I'll do one thing here. So what is unit of energy? Coefficient of viscosity m L to the power minus 1 to the power minus 1. So that is not happening here. So force constant K is equal to F by L. ml, so ml to the power minus 2 by L. So that is also not true. What I have got here. Okay, let me just check with this. Okay, whatever informations I have been given, like options I have been given, let us do with that. Okay, that will be better. So I have got this one anyway. Okay, so look, this energy density will be actually work done ml t to the power minus 2 into L. This will be work done, so ml square t to the power, so I can write, see, ml square t to the power minus 1. So this will be your work done. Okay, better not to go with that direction. So this is energy ml to the power minus 2. So this is L square divided by L cube. So this is ml to the power minus 1 to the power minus 2. So this is the answer actually. So my advice will be to write down the, like, you first find out what is the dimension you are getting here. If you are not understanding what is the term with the dimension you get, then better to cross check with the options. See, this one actually is becoming ml to the power minus 1 to the power minus 2, which we have got. So energy density will be the dimension of the x. Okay, all right. Let us go to the next problem. So this is also a very nice problem. A small ball from this ball of mass m, a small ball of mass m is thrown upward. So this is thrown upward, small ball, okay. But anyway, it has certain mass m that is given upward with the velocity u from the ground. Okay, this is thrown from the ground. The ball experiences a resistive force mk v square. Okay, mk v square. So it is experiencing a resistive force. So whenever you see the resistive force, so resistive force is actually always acting in the opposite direction to the motion of the object. So this is resistive force. Resistive force. Okay, where v is its speed. Okay, v is its speed. When the speed is v at any instant of time, the resistive force will be mk v square. The maximum height attained by the ball is how much? That you have to find out. See, you have to find out the maximum height attained by the ball. So how do you get that? So to get that, first of all, we have to write down. See, you have been given certain velocity, right? So you have been given velocity, and see there are two forces acting on this. One is mg in this way. Another one is the resistive force, that is mk v square. So these two forces are acting in the opposite direction, right? So you will have eventually negative accelerations, okay? Negative accelerations, and at the maximum height you will be actually reaching when your speed is 0. So at the maximum height, speed will be 0. Let me then take the situation where the speed is v. At that situation, what is the acceleration? Acceleration, I am taking the modulus of that, is g plus, so this is the total force, net force acting on the object. So the acceleration will be in the negative direction or in the downward direction, but so that's why I'm taking the modulus here, and this is k v square. Okay, see, this one is a negative quantity, so I can write this as, see, in terms of, see, I have to find out height, right? So acceleration can be written, so it's v dv dx, v dv dx. So in place of x, I can write v dv dh, that is equal to g plus k v square. Okay, now look what I can do. I can strike one v from both sides. Is that possible? No, let us not do that. Otherwise, we'll be in trouble. Let us do in another way. Let us integrate this. Okay, so this is anyway minus, see, I can write v dv divided by g plus k v square, and that is equal to dh. And I can take the integration, and look, the integration limit I will take here, since there is a negative sign in the velocity side, I'll take this as u to 0. Okay, so v dv g plus k v square. Okay, k v square, and on the other side it is 0 to maximum height. Okay, with the minus sign, h max, let us say, and this is dh. Okay, so here, see, if I have to do this integration, I have to actually consider this g, replacement you have to do to be, let us say, this is y. Okay, so if I take the derivative, this is constant term, this k is also constant, so we'll get 2v k dv is equal to dy. So we have v dv is equal to 1 over 2k dy. Okay, I'll just do the integration first, and then after putting the y to be this one, then I'll put the limit. So I have changed the parameters. So v dv is equal to 1 over 2k dy, and this is y, right? And other side I can get minus h max, and see the limit will be here. If I put this v is equal to 0, I'll get y is equal to g, and if I put v is equal to u, I'll get something, but I'm not putting the limits. Let me just write in this way first. So integration this is 1 by 2k ln y. Okay, now this is, see, there will be c then in infinite integral. Okay, not definite integral, right? So this is h max. All right, so ln g plus excuse me, k v square, I'm just putting the value of y, and this has got a limit u to 0 minus h max. Okay, see, if you put this limit u first, okay, sorry, 0 first, then what I'm going to get, I'm going to get 1 by 2k ln u is equal to 0, this v is equal to 0, v is equal to 0 means I'll get ln g minus of u is, v is equal to u, I'll put, so ln g plus k u square, right? This is equal to minus h max. Okay, so if we rearrange this, so this 1 by 2k is common. See, I'll just want to make h as positive, then so I have done the integration part. Let me write what I have got. Okay, so then I'll compare with the options here. Let me clean everything here. So I have got h max. If I write this, so I have 1 by 2k here ln g plus k u square minus ln g. So this I will write as division. So ln g plus k u square divided by g. Okay, then what I get? 1 by 2k ln 1 plus k u square by g. So this is the answer, 1 by 2k. So option C will be the correct answer for this question. Okay. Now let us go to the next problem. This problem says a person pushes a box. A person pushes a box on a rough horizontal platform. Okay, platform surface, anyway, the horizontal platform surface. He applies a force 200 Newton over a distance of 15 meters. Thereafter, he gets progressively tired, and his applied force reduces linearly with the distance to 100 Newton. The total distance through which the box has been moved is 30 meters. Then what is the work done by the person during the total movement of the box? See, this problem can be very much represented with this figure. Look, this figure. So initially the person was pushing a box on the rough horizontal surface, so obviously there will be frictional force. So he was pushing with a constant force 200 Newton up to a distance 15 meter. Okay, and then thereafter he gets progressively tired and applied force reduces linearly to 100. Look, this is constant force up to 15 meter, and the remaining 15 meter the force applied by the person is linearly reducing, and finally it becomes 100 Newton when he already covered a distance 30 meters. So then this force, you look, this is actually reducing from 200 to 100. Okay, so here to find out the total work done during this journey of the person, I have to find out what is the area under this. Okay, area under this. So area under, so work done here, total work done will be area under the FD curve here, FD curve. So work done will be area under FD curve. D curve. Okay. So to find out area under FD curve, see first area, you know, this is a rectangle, so you will get 200 Newton into 50 meter, and the remaining part is actually this. This is a trapezium. Okay, so you have to find out the area of this trapezium. We can do in two ways actually. See, I can find out this first. That way also we can do. This is a rectangle, this is triangle. I can do. Let me just find out that. Okay, so see, this rectangle is actually this is 15 into 100 plus half into base into height. Height is 100 again. Okay, so then look what I can do. Okay, let me just find out this. So this is 7.5 here. So this will be 1500 plus this is 750. So you get what? 0, 5, this is 2, 2. And here you have got, so this much is this, and you have got 300. Okay, 15 to the 30, another 2 plus this. So what you get is this 2, this 3, so 5250. This is joule. So option C will be the correct answer for this question. So here actually you need to find out this clue actually. Okay, you have to solve this problem you must be able to draw this FD diagram. Otherwise you will not be able to solve this problem. Okay, and see here it is progressively reducing. Okay, it is not suddenly reducing. The force is not suddenly reducing to 100. It is progressively. That means slope is actually slowly it is decreasing. Okay, so that is where actually was the point in this problem. Okay, that is what. So you need to practice this kind of problem so that you can understand the question. Okay, all right, we have the last question for today's session. So this question says a body is moving in a low circular orbit about a planet of mass m and radius r. The radius of the orbit can be taken as r. Radius of the orbit also can be taken as r, and the planet has radius r. Lower orbit, okay. Then the ratio of the speed of the body in the orbit to the escape velocity of the planet. See, escape velocity, if you know the formula, you can directly write down. Otherwise, see, I'll just find out the orbital velocity first. Orbital velocity is actually half m. I'm sorry, is mv square. Mv square by r. If this is here, this is capital R itself, is equal to gmm by r square. So this r, I'll just do this simplification. So v, this is orbital velocity. Orbital is equal to square root of gm by r. Okay, if you don't remember, if you remember, you can directly, you should not lose time. Okay, you should directly do this. Okay, you can directly write gm by r, square root of gm by r. Okay, better not to waste time. Okay, if you can't remember, then you have to find out the formula for this orbital velocity as well as the escape velocity. Escape velocity most of you know, but still I'll just tell you how to find out if you don't remember. See, in case of this escape velocity, see, you have to directly write the conservation of energy. Conservation of energy at the surface of the planet you have. See, you have given certain velocity, suppose v e escape velocity. So half mv square is the kinetic energy, and potential energy will be gm m by r. This is equal to 0 because at infinity potential energy is 0, and at infinity there will be no kinetic energy as well, no velocity as well. Okay, so then this is the, see, this is the way to find out. Now v square is equal to 2 gm by r. Okay, then you know what is this ve will be square root of 2 gm by r. Okay, now things will be easy. See, we have been given to find out the ratio of the speed. Okay, ratio of the speed of this body in the orbit to the escape velocity. Orbit is this orbital divided by ve. This is what we have to find out. So look, I can write root gm by r, and this is, see, in the denominator, so r will be in the numerator and here it will be root 2 gm. Okay, so you know this r, this r, gm will be cancelling out. This will be 1 by root over 2. So option B will be the correct answer for this question. Okay, so that's actually this question is also from the 4th September paper 2020 shift 1. Okay, all right, so with this we'll stop it here for today. In the next session we'll continue with the 4th September papers. Okay, so thank you for your patience. Bye for today.